Imagine this, you're in a bustling greenhouse where maintaining the perfect temperature and humidity levels is essential for plant growth. Now envision deploying this IoT marvel within your greenhouse, it continuously monitoring and fine-tuning the environment. And today, we're going to dive deep into the details of this design. And if you want to build yourself a cool gadget like this and many more, be sure to check out today's sponsor, PCBWay. If you're looking to turn your electronics projects into reality, PCBWay is the place to be. They offer top-notch manufacturing services, fast turnaround times, and excellent customer support. So whether you're a hobbyist or a professional, PCBWay has got you covered. Check them out today and turn your ideas into reality. Today, we're diving deep into the fascinating world of IoT devices. Specifically, we'll be taking a closer look at a remarkable little gadget that senses humidity and temperature in its environment. But before we jump into capturing the schematic and layout on the board, let's start by understanding the block diagram representation of this innovative IoT device electronics design. Here you can see the block diagram of our IoT device. It's a compact, portable, 1 square inches PCB designed for both commercial and industrial settings. So what does it do? Well, let's break it down step by step. First up, we have the USB connector. This little port serves a dual purpose. It not only powers the device, but also provides a two-way communication channel to the host. The USB interface is incredibly versatile. It allows us to program the board over USB, making it user-friendly and easy to update with the latest firmware whenever we want. Plus, it also lets us send the sensed data over USB to a host computer for any potential further data processing. That means we can remotely monitor and analyze the environmental conditions in real time. So now that we're looking at this USB connector, we gotta ask the question, what happens if our main USB interface goes down for some reason? Well, that's where this comes in. The redundant SWD programming header. It's here for debugging and programming purposes, ensuring that our device remains accessible even if the primary USB interface encounters issues. So now that we talked about the programming and interacting with this device, now the more important part of it is power. USB power is crucial, but it's not just about plugging and hoping for the best. So that's why I've included a filtering and conditioning stage to obtain a clean, correct voltage level for downstream devices. As you can see, we have the STM32 microcontroller and the sensor that's fed directly from this power conditioning circuit that we're gonna dive a little deeper a bit later. So now this power conditioning stage ensures that the main STM32 microcontroller and the temperature and humidity sensor IC receives stable and reliable power so they can operate efficiently and provide accurate data. And with that, there you have it. That was a concise overview of this little IoT device electronic design. And now it's time to move on to the next step, capturing the schematic and laying out the board based on this system level understanding and this block diagram. Let's get in. So here is my USB connector. As you can see, this J1 is my USB connector where I have the power from USB, I have ground, and I have the main two data lines, which is negative and positive. And the pin out is pretty straightforward, just 4 pins. And this is a typical USB 2 header. So now for the power, we always put a decoupling capacitor to basically filter out some of the noise that can exist along the line. And we're gonna also have 2 small capacitors to decouple any potential noise or harmonics that can exist along the data line as well. Since again, this is a external connector, which it connects to external devices and people can handle it, it's recommended to add some sort of an transient suppression component, which in this case is a EST diode or TVS diode as we call it. And this particular component protects both the data line as well as the power. And we also have this ferrite bead. The purpose of this is also to filter out some of the harmonics, but in a more specific frequency range. Basically, this ferrite bead as well as this capacitor will form an LC filter, which is used to filter out the higher frequency noise that exists on the power line, which in this case, I'll call it the V-bus. So just moving on, we can see that I have these 2 markings in here. You can select these 2 on Altium just to indicate that these 2 pairs are meant to be traced as a differential pair. And one way that you indicate that on an actual net is to having this D underscore N and D underscore P. So underscore N underscore P indicates that the associated net name, which is D in this case, as for data, are associated together as a differential pair. So that's why I call it DN. And then this DN, we're going to get to it in a bit. It's going to basically be fed directly to this SEM32 microcontroller that we discussed in the block diagram.